Hello everybody, welcome back. It's Mr. Breaker here with our 8th installment in AP Statistics. We are looking at Chapter 2, Section 1 right here, Transforming Data with Density Curves. We start off this lesson with a little classroom activity that we wouldn't have if everyone was in class, but I'll go ahead and try to make the best of it by doing it by myself, and just so you can see everything that this lesson really entails is really in this first example. So please pay attention through this because it's going to allow you to answer all of the remaining notes and become an expert at transforming data with density curves. It's just with this one example. Okay? So the first thing I would do when y'all would walk in the classroom, I'd say, hey, go ahead and guess the width of the classroom in yards. Okay? So let's go ahead and just say we have 10 people that just walk through the door and they're going to guess. So let's have, say, I think it's 10 yards wide, maybe 20, 15, 12, 17, 25, 13, 17, and 15, and 14. All right, so those are our first 10 guesses of you all saying, you know what, Mr. Brager, I think this is the width of our classroom. I'm like, okay, let's go ahead and make a dot plot of this just so you can see what's going on. This is everyone's guesses, and they're in yards. Looks like our lowest number is 10, highest number is 25, so let's go by twos. 16, 18, 20, 22, 24. We could probably figure out what 25 is after that. So again, making a dot plot. Well, 17, 25, 13, 17, 15, and 14. All right, so there's our dot plot of everyone's guesses. Easy stuff so far. This is all things that we've done. Great. A couple things I would like you to be able to find, just for fun, before we move on so you can kind of see how all this works, is let's go ahead and find the average and the standard deviation. A lot of people work with those, like to work with those numbers, so we'll go ahead and use it. X bar is a measure of center, and the standard deviation, SX, is a measure of spread. Okay, so how can I get my calculator to help me out with this? Remember that we were in stats, so if you hit that stat button and you just hit enter on edit, we're going to go ahead and put this into our list in our calculator. You might already have numbers in here from L1, so remember all you have to do is just hit scroll up, clear, scroll back down, and they're gone. So I'm going to go ahead and put these in. Got all those 10 numbers in. How do you find the X bar and the standard deviation again? You're going to hit stats and go to calc. So stat, calc, and one variable statistics. That's going to give me all the information that I want. It's pulling my data from list 1, so we're good to go. And it looks like our average, or X bar, is 15.8, and our standard deviation was 4.29. So again, this is just like a little review. This is all things we've done before. Great. What happens if I said, you know what, let's take everyone's guesses and let's compare them to the actual. All right, let's say the actual distance is 16 yards. Okay. Well, let's go ahead and make a dot plot of everyone's error. So we'll say the error, and let's go ahead and say it's their guess minus the actual. Okay. So let's go ahead and write those numbers down just so you can kind of see it. So this is like our first graph over here. This will be our second graph. So if I take all these and do guess minus the actual, 10 minus 16, you're looking at negative 6. 20 minus 16, you're looking at a positive 4. And just go down the list and subtract these from 16. All right? Negative 1, negative 4, 1, 9, negative 3, 1, negative 1, and negative 2. Alright, so your guess minus the actual. All these numbers minus 16, all the way down. Let's go ahead and make a dot plot of those. Looks like our smallest number is negative 6, and our highest number is 9, so we'll go by 2's again. So negative 6, negative 4, negative 2, 0, 2, 4, 6, 8, and well, you can kind of guess where 9 is. So let's go ahead and make a dot plot of these numbers. So again, negative 6, 4, negative 1, -4, 1, 9, -3, 1, -1, and -2. Alright, so again, we just make a dot plot. We just did guess minus the actual, made another one. Let's go ahead and figure out the average and the standard deviation of this one. So, making you calculator savvy. Calculator can do this for us real fast. Just so you know, if I went back to my stat, hit the stat button, and went back into my list, so I just hit enter on edit right there. Alright. I can scroll up with my cursor highlighted in L1. Nothing's blinking yet, but if I hit enter, notice that this is blinking down here. And if you would hit second L1 is 1 down here. See how that L1 is right there? If I hit second L1, I can take all those values in list 1 and subtract off 16, just like I did on paper. And notice these were the exact same values that I just had written on the piece of paper over here. Okay? Have my calculator do the average and standard deviation real fast. So average standard deviation, that's calc, one variable statistics. Still pulling the data from list 1. And notice my average now is -0.2 with a standard deviation of still 4.29. Okay? So, fair enough, right? This is good. And last one we'll do is that, then we'll be able to answer all of these, is that what happens if I took all of these errors, which we have right here, -6, 4, -1, blah, blah. And again, these are all in yards. But what happens if I said, let's plot the error in, which is again, guess minus the actual, but let's put it in feet. Okay? So let's take all these numbers right here. This will be our third graph. This is kind of like our first graph, second graph, and our third graph right here. What happens if I took all these numbers in yards and multiplied them by 3 so I could get them into feet? Well, this would be -18. This would be 12, -3, -12, 3, 27. Multiplying everything by 3 so I can get them into feet. -9, 3, -3, and -6. So it looks like the smallest number is -18. Right? So -18, and we go all the way up to 27. Alright, so let's go ahead and start at -18. Let's go up by, 6's. So this will be -12, -6, 0, 6, 12, 18, 24. Alright, so we can kind of guess where 27 is going to be. So making a dot plot of all these. This is our last dot plot for today. It'll be fun. -7 is going to be way out there. -9. 3. -3. -6. Alright, so we did all that fun stuff. And let's go ahead and find the average and the standard deviation of this one, just so you can see with that right now. So again, I have all these numbers in my calculator, so if I went to stat, edit, just hit enter, can I take all these numbers right here and multiply them by 3? Well, let's scroll up, highlight list 1. We're going to hit enter and do the second one again. So we take everything in list 1 and we're going to multiply it by 3. So those are all the exact same numbers I just had written down right here on the top of our paper. Okay, and I can do the one variable statistics now, figure out all this fun stuff. So calc, one variable stats. Our average is now -0.6 and our standard deviation is now 12.87. Okay. Well, let's answer these questions. And you'll see why we did these 3 right here. What is the effect of adding or subtracting a constant from each observation? Well, in our second graph, we subtracted 16 by everything. Okay, we took our actual values and we subtracted 16. So from going from the original graph to this one, what changed? Did the shape change? No, shape didn't change. You still have like 4 dots, 2 humps, and a dot spaced out. 4 dots, 2 humps, and dot spaced out. I mean, like, shape didn't change. Did the standard deviation change? No. So measures of spread did not change. What did change? It looks like measures of center changed. when we add or subtract a constant. So what is the effect? Measures of center change. Okay, and again, that's the mean, median, and the mode. Shape does not, and measures of spread does not. Okay? What was the effect of multiplying or dividing each observation by a constant? So we get all these data, this data in our calculator, the -6, 4, -1. So we have all these numbers. And then we took all those numbers and we multiplied them by 3 to change them into feet. So what happened when we multiplied by 3? And it could be or division. What happens when we multiplied by 3? Did the shape change? No, it looks like we still have 4 dots, 2 humps, dot spaced out, 4 dots, 2 humps, a dot spaced out. Shape didn't change. It might have just gotten a little bit more spaced out based on our scale, but the shape itself did not change. All right. Did the mean change? Well, sure. It went from -0.2 to -0.6. So the mean changed. Did the standard deviation change? Of course. We went from 4.29 to 12.87. So what happens when you multiply or divide? Center changes and measures of spread. So I would say measures of spread, or we'll keep it uniform, measures of center and spread change. What never changes? Shape. It doesn't matter what you do, adding, subtracting, multiplying, or dividing. Shape never changes. Okay, keep that in mind. Shape never changes with transformations. Now, where you need to be is because this one example right here kind of took a long time. Most of the time, you're never going to have this data in your calculator to put in there and do modifications in your list to calculate the new mean and standard deviation, all that other fun stuff. And you're not really going to have time to draw 3 separate dot plots, make sure everything's labeled, and be able to answer all these questions. You have to be able to go from here, the average of 15.8 to a standard deviation of 4.29, and go all the way over to this without drawing any graphs or plugging numbers in your calculator. I just want to show you what would happen. If I had my calculator in front of me and I was like, you know what, I know the original set of data is 15.8. Okay? What we did right here is that we subtracted 16, we subtracted the actual amount, and then we multiplied by 3. What section 2.1, transforming data, is all about is, do you understand that adding or subtracting changes means? Sure. So the first thing we did was subtract 16. So does subtraction change means? Yes, I want to subtract 16. Notice that was our average. I didn't even have to plug anything in my calculator and draw another dot plot. I understood that subtraction changes means, so my mean is going to change by subtracting 16. What did we do then? We took all of our values and multiplied it by 3. Okay, well, does multiplication change means? Measures of center and spread change. So means a measure of center, so it's going to change as well. What if I just took this number and multiplied it by 3? I get -0.6. So I went from here, 15.8, to -0.6 without having to type anything in my list or draw another graph, because I understand what adding and subtracting, multiplying and dividing does to means. Same thing for standard deviation. Our original standard deviation was 4.29. So if our original standard deviation was 4.29, and then we subtracted 16 from everything, did our standard deviation change? No. So does subtraction change standard deviation? No. I wouldn't even do it. I would just kind of X this out, and I don't even do this because I know subtraction does not, change measures of spread. However, we took all these numbers and multiplied them by 3 to change them to feet. Does multiplying and dividing change measures of center and spread? Yes, it does. So what happens if I just took 4.29 and multiplied it by 3? Notice I'm at 12.87. I went from 4.29 to 12.87 without having to put anything in my calculator, draw 3 dot plots. I understand what adding and subtracting, multiplying and dividing does to measures of spread. Okay? Adding and subtracting doesn't change, but multiplication does. So that's why the only operation I did was multiplying. Okay? Big example right there. Little fun fact, shape never changes. Keep that in mind. All right? So let's look at this example right here. In 2010, taxicabs in New York City charged an initial fee of $2.50 plus $2 per mile. In equation form, the fare is $2.50 plus $2 for every mile. At the end of a month, a businessman collects all of his taxicab receipts and analyzes the distribution of fares. The distribution was skewed to the right with a mean of 15.45 and a standard deviation of $10.20. What are the mean and standard deviation of the lengths of his cab rides in miles? All right, so what's the mean and standard deviation basically in miles? Well, I don't have all of his cab fares from a month, so I can't put this in my calculator and do what we're doing up here and modify the list and draw a bunch of dot plots. I don't have any of that. All I know is that my average fare, okay, was 15.45, and I know that my standard deviation of the fares was $10.20. Okay, put money signs in front of these. Could I use this equation, which is fare equals 2.5 plus 2 miles? Could I use this equation right here to figure out the average in miles and also the standard deviation in miles? Well, of course. If I plug in a fare, what am I going to get back? I'm going to get miles because that would be my unknown. If I plug in the standard deviation fare into the fare, I'm going to get the standard deviation in miles. So let's go ahead and do that. If I plugged in 15.45 right here, if this is the average fare, I can plug in the average fare right here. This equation is going to give me the average amount of miles because this was the average fare, so this is going to be the average amount of miles that I drove to get that average fare of $15.45. But here's where you got to pay attention. I plugged in a measure of center, which is a mean. If I said solve for X or solve for miles, you got to ask yourself, does subtraction change means? Well, yes, it does. All right? Yes, it does. So this would turn into what? 12.95 equals 2 times miles. And if I said solve for miles, what would you do? You divide it by 2. All right? So what is 12.95 divided by 2? You're looking at 6.48. In other words, okay, miles is 6.48. In other words, you drove 6.48 miles on average to get an average fare of $15.45. And I didn't even have to do any of this stuff up here. I didn't have to plug this into my list. You know, I didn't have to add 2 and then, you know, I multiply by 2 and then add 250. I was able to just go from here to here really, really quickly. Okay? What happens if I plugged in the standard deviation of fare into this equation? Am I going to get the standard deviation of miles back? The answer to that question is yes. All right, so I'll kind of continue this example right here, and I'll run out of room. But if I plugged in $10.20 into this equation, all right, so this is now standard deviation. This over here was means. Okay? If I plug this in, I'm going to get the standard deviation in miles driven. So solve for X, solve for miles. First thing you got to ask yourself, if I subtract 250, does subtraction change measures of spread, which is standard deviation? No. So I'm not even going to pretend it's there. I'm not even going to do it because I know subtraction does not change. We're still solving for X though. If I divide by 2, does division change measures of spread? Yes, it does. So what we just discovered right here is that if your average fare was $15.45, you drove an average of 6.48 miles. If your standard deviation of fare was $10.20, your standard deviation in miles driven was 5.1 miles. Okay? If your standard deviation of fare was $10.20, that means your standard deviation in miles driven was $5.1 miles. All right? Good. So we used our formula right here to do transformations of data without plugging it into our calculator and doing all the hard work. All right? These would be your answers right here. Okay? This last example right here. If the businessman standardized all of the fares, what would be the shape, center, and spread of the distribution? Well, first of all, standardized score. That's a z-score. If you don't know what that means, please put that in your brain. Standardized means they're talking about z-scores. So if the businessman standardized all the scores. In other words, they put them into z-scores. What would be the shape, center, and spread of the distribution? Okay, well, let's think about that for a minute. If we standardized all the fares, what would be the shape, center, and spread of the distribution? Okay, well, let's talk about the average. First of all, you got to remember what a z-score is. The actual minus the mean over the standard deviation. Okay? The only numbers that we have to go off right now that we know of is, we know the mean is 15.45 and the standard deviation is $10.20. Okay? If I plugged in the actual mean, okay, because that's all we know. If I plugged in the actual mean, which all we know again is 15.45, that was the actual mean, and I plugged it into the z-score formula with the mean and standard deviation that we're already using, notice what happens. Okay, 15.45 minus 15.45 is 0 over 10.2, which you get 0. What does that mean? Your average is 0. That's your average z-score. In other words, what I'm trying to get you to understand is that when you standardize scores, no matter what is your average always going to be of all z-scores? It's 0. Okay? Your average of all z-scores is going to be 0. Hands down. If we did standard deviation, it really works the same way. I don't want to get you lost in all these algebraic proofs right here, just because it's really not needed. What you need to understand is if you standardize the scores, your standard deviation of all z-scores is going to be 1. So just keep that in mind. This is kind of like another fun fact for today's lesson, is that the average of all z-scores is always going to be 0, and the standard deviation is always going to be 1. Okay, and if you remember Algebra 2, we drew this a lot. Okay, but notice, even though we subtract and divide by something, what never changes? The shape. Okay, the shape never changes. So if this businessman standardizes all the scores, okay, your mean is 0 and your standard deviation is 1 every time because it's a standardized score, z-score, the average is 0 and the standard deviation is 1. But the shape, in this case, is still skewed right. I know we subtracted and divided, but it doesn't matter. Shape never changes. Did they tell you right here that the distribution was skewed to the right? Yes. So, standardizing by adding and dividing does not change the shape. It is skewed right. What's the average of all z-scores? It's 0, and the standard deviation is 1. I hope you all enjoyed today's lesson. I'm trying to keep it light and entertaining at the same time. All right, we'll see you tomorrow, and thank you very much for watching.